Here's the graph of f of x given to us, and we want to sketch the graph of y plus 4 equals f of 1 half x plus 1. So the first thing I'm going to do with this equation is I'm going to rewrite it so it's y equals. We've been dealing with things outside of the function all on one side of the equation. I'm also going to look and notice here, because we made a special note yesterday, that things need to be in factored form, and this is already in factored form. Something that I'm doing here with my brackets. Do you notice how I have like little brackets and big brackets? Visually, that helps you see what goes together better. You can make them all the same size, but that sometimes can get confusing. So I'm using the big brackets to show that all of this is inside, and it's in factored form, and then I'm moving the 4 to the other side. Next, I'm going to go through each of the things that appears. There's a 1 half, there's a 1, there's a minus 4, and I'm going to label them what's happening. Horizontal or vertical, stretches, compressions, translations. What does that 1 half do? Can you see that that 1 half is inside the function? Inside the function is horizontal. It's multiplying by x, so it's either a stretch or compression. In this case, because it's a half, you would multiply your x by 2. The plus 1 inside it, so it's horizontal. It'll be a horizontal translation. This will go 1 left. And finally, outside is vertical. We are going to go 4 down. I also hope that you recognize the graph that was given to us as one of our graphs from our blue page. This is the 1 over x graph. If you have your red pen, I would like you to draw in the asymptotes at y equals 0 and x equals 0 and label them. They've labeled 2, 0.5 and negative 2, 0.5. I'd like you to label the more typical points that you would do on your reciprocal graph are 1, 1 and negative 1, negative 1. So once we realize what we all need to do to show our work, we're going to take our original points, so 1, 1, and negative 1, negative 1. Draw our arrow diagrams, and because we have stretches as well as translations, we always do our stretches and compressions first, followed by our translations. And so above these first set of arrows, I look, what kind of stretches and compressions do I have? Only one, that x is getting multiplied by 2. What kind of translations do I have? I have 2 of them, 1 to the left, and 4 down. So I label those above my arrows, and from here, I can figure out where those points are going to go. X by 2, that'll change this to 2, and negative 2, the y values aren't changing. Then 1 to the left, and 4 down, and I'm making sure I'm double checking my mental math and not going too fast. And the other thing you're going to do with the reciprocal graph is you're also, after doing your 2 points, also list your asymptotes. We have 2 asymptotes, x equals 0 and y equals 0. And as far as the arrow diagram goes, in this case, we can just do one big arrow, because multiplying, when it's at 0, can you see that multiplying x by 2 won't make a difference? Multiplying y by something, if it started at 0, also won't make a difference. The only way that this vertical asymptote is going to change is if you shift it left or right. We are going 1 to the left, so this one that's at 0, if I move it 1 to the left, can you see that it will become minus 1? With your horizontal asymptote at y equals 0, the only thing that's going to affect that is if you move it up or down. We're moving 4 down, so it's going to become y equals -4. Now, I'm going to suggest whenever you are going to graph your new function, sometimes they're going to ask you to graph it on the same graph. Often it's going to make sense to just quickly make a new graph, because if you put everything on the same graph, especially with asymptotes, it's going to get too busy and it's going to be hard to see what the final answer is supposed to look like. So first thing I'm going to do here is I'm going to draw my asymptotes. I have a vertical asymptote now at x equals -1 and a horizontal one at y equals -4. I'll label my points. I have a point at 1, -3. Draw the dot and label it, and a point at -3, -5. And have enough information to draw my graph towards the asymptotes with the right shape. I'm going to reread the question, make sure I didn't miss anything. Here's the graph, sketch the graph, I've done the sketch. Oh, state the domain and range of each function. So I need to do the domain and range of my original graph. And when talking about domain with the 1/x graph, the easiest way to write the domain is just say what it can't equal. X can't equal 0. This would be the set notation way to do it. Sometimes you'll see the set notation way just like this. Sometimes they'll add XER afterwards, saying it's everything except X can't equal 0. Because that's where we have that vertical asymptote, that non-permissible value. I will show you this in interval notation because it's interesting. You have no smallest value, so you start at -infinity and you go to 0, but you can't include 0. And then you start on the other side of 0 and go on forever the other way. And so we have 2 separate intervals with a break. In interval notation, we write it as 2 separate intervals, and we put a big U in between, and that U says it can be in this interval or this other interval. Same thing with the range. There's only one value it can't equal. Y can't equal 0. And you could do the same thing with interval notation. But I'm just going to keep it simple. That's the easiest way to write it. For your blue graph then, for my domain on my blue graph now, x can't equal -1. And for my blue graph now, y can't equal -4. One of the things that's sometimes confusing in this first unit in transformations is the notation, getting used to how to write things. And this is a great example to look at that right now. So I would like you to, we're going to make a chart here. This question was done in function notation. And sometimes we do questions in explicit notation. So we're going to look at this one just to talk about notation. When you get a question in function notation, they give you your original like this. Y is some function f of x, and you don't know what it is. That's what we had in this question, right? If we turn up to the beginning, it says, here's the graph of y equals f of x. So this question is in function notation. And then they say, sketch the graph of, so we're making an image graph, and that image graph is in function notation. It was like this. That's the image graph in function notation. Now, in explicit notation, we can use explicit notation if we recognize the graph. And this one we did. It was from our blue page. It was the 1 over x graph. So the explicit notation for the original would be y equals 1 over x. That's the actual equation of the original one. So what we notice, if we compare explicit to function, is that in function notation they have f of x. In the original they have 1 over x. In other words, the f of x is equal to the 1 over x. Does that make sense? As far as looking at the two equations, that's what's been substituted in. And this, what I've written in blue, is what is going to allow you to switch from one notation to the other. So if I had this same question, the image would look like this. Okay? And I'm going to use my function notation to help me write my explicit notation. Now, how do functions work? Here, in the blue, I have f of x equals 1 over x. If I asked you, what's f of 2? You'd have no problem. You'd plug in 2 for x, you'd say it's 1/2. If I said, what's f of 10? You'd have no problem. You'd say f of 10 is 1 over 10. You know that with a function, that whatever I tell you inside, you would just replace the x with that. F of 3, 1 over 3. And I could get creative. I could say f of k. Ooh. Can you see that that would be 1 over k? I could use negative numbers. F of negative 7. It would be 1 over negative 7. Okay? What is interesting, though, is when we get creative, all of a sudden, our brains sometimes stop working. I could do f of Sam, and we would get 1 over Sam. That's totally allowed. Okay? It's weird, but it's totally allowed. So now, if I have the function notation here, what's inside now is this. Can you see that that's now inside f? And so, if I can do 1 over Sam, I can definitely do 1 over this. I'm going to get 1 over 1/2 x plus 1. And I still have the minus 4 outside the function. That's still going to be minus 4 outside the function. In this example in particular, the function notation is way easier to see what's happening. It's so easy to see this 1/2 inside the function x by 2, this 1 inside the function 1 left. Can you see yourself getting a little thrown off by the actual equation? This 1/2 is where the x is, it's inside the function. This would mean multiply x by 2, move 1 to the left, 4 down. This image equation in explicit notation is exactly the same question as in function notation. But the function notation in this case is easier to work with. Sometimes the explicit notation will be easier to work with. But if you can see the connection between the two and how they're like the same thing written in different ways, then your understanding is going to be a lot better. Okay, questions for practice on this one? Brought to you by Slurpee, 7 and 11.